Okay, well, I'll get started, and as people come in, people leave or whatever, right? But I'm really, this is an idea. It's the germ of an idea. It's not. This isn't. You're not going to learn anything very much apart from some kind of goofed up, screwed up concept of how industry works, maybe, right? Okay. Or how, and then the dysfunction of industry. And it's an idea about how could we use VSM and other stuff to actually fundamentally help us understand how we can make the process industry specifically better, right? And really what I'm hoping to do, this is always a great crowd, albeit it's not great small crowds.
Quality.
Yeah, quality crowd. Quality crowd. And it's really, this is a blatant attempt to scrape the best of what's in your minds and then plagiarize them mercilessly in terms of trying to make a difference, okay? So just a real quick introduction. I'm John, you both know Penny. You guys probably, I don't know if you met Penny yesterday or not. He was here yesterday in my stead. I was down in London running a workshop for government, actually, which I need to talk to you about because it was a lot of fun. There was a guy there who did his MSc on the emergency response to the floods in the Somerset Plains. So, yeah. But I was down there, so we're tag teaming. Penn's currently in a coaching workshop up in South Shields now. So, but essentially, Penny and I have a kind of a mission, which is to try and help engineers, scientists, technical technologists, including software people, better get to grips with complex systems. I call it humanizing complex systems. So it's not giving shitloads more theories so that the world's even more complicated. It's how, as a human being, do I allow myself to be a human being and interact with a complex system to be more effective? And the reason we do that is because it makes engineering more effective, right? It means that we can actually solve the big societal problems we can solve rather than worry about designing heat exchangers or electricity transformers. Come on in, John. So that's kind of who we are, and that's what we do, right? So the origin story of this presentation, right, is going to be, it is really sort of why am I actually telling you? Are you confused?
There's not enough description here, so I just came to see what it is.
It's okay. So
probably can just
if you give it to you'll get there real fast, right? Yeah. It starts with these two people. Martin talks about the neurology of business, right? It's a model that I really buy into. Which one, John leaves?
No. It sounds fascinating, but I've got all my stuff here anyway.
Okay.
I'll get out of your way.
Okay. So, I mean, I've listened to Martin's description, particularly about the idea of the neurology of the business thing from. It's all right, guys, don't worry. I want this to be informal, so I'd actually sooner not be sounding things. But so take that idea, which I find quite enlightening, and the way that Martin frames that up, combined with the delights of having become a certified VSM coach on Angela's course. So this is these two things come together and appear to address a challenge that I've kind of seen in the process industry throughout my career. Right? But I want to acknowledge those two in terms of this isn't new thinking, right? It's about how can we take those two kind of concepts, which are very closely related, and say, well, okay, turn them into something of use to solve a pretty fundamental problem for these industries. Right? The process industry, and being very specific about process industries, Martin's done loads of work around manufacturing, discrete manufacturing. And I think the ideas are pretty well built out and well understood there. And it's probably also fair to say that in the discrete manufacturing world, digitalization has had a really profound effect, arguably a disruptive effect. Now, I would argue that's because we've gone from a world of making 1,000 red cars on Monday and 1,000 blue cars on Tuesday to a point where today every individual car running down a manufacturing line is fundamentally different. And what they've done is they've taken time as a day and progressively shortened it to the point where they are effectively running in continuous real time just by shortening time horizons. Now in this industry, these industries, we can't do that because things don't start and finish. This is molecules running through pipes, right? Particularly in some of these big commodity industries, it's molecules running through pipes, it's continuously flowing. So there isn't a time horizon or a lot size or a batch size that we can reduce. So there's ideas like lean manufacturing, just-in-time manufacturing, Kaizen, Kanban, and a million other things tied up to manufacturing system. None of those really translate cleanly into this industry, into these industries. As a result of which, these industries have sat and looked at digitalization, spent fortunes, but accomplished precious little, right? And that is kind of the story of my career and arguably the story of my life, right? So my hope is that today I'm going to get some ideas from folks here.
But you've had some of the shed loads of money that didn't lead anywhere, is that right?
Huh?
You've had some of the shed loads of money that they spent.
Yeah, it's fair to say that my pension is probably largely founded on some of the shed loads of money that has been spent on getting nowhere.
Okay,
right?
very good.
Right. I'm not sure that that's fair or not. I just wanted to say that one of the things that this is a model that I've created over the decades I've spent working in and around this set of industries that say actually we can characterize all process industries at one level, but it's pretty abstract and pretty esoteric. But when we break it down and understand what each of them in turn does and what their underlying business models are, we can take that generic model and customize it and tailor it into something that's a practical and pragmatic use to an electricity generator, or somebody that runs long distance pipelines, or somebody that's manufacturing ethylene and polyethylene, right? So what I envisage, and I could get this is almost coming to the end, right, is something, this process industry neurology model or framework that is pretty abstract at its generic level, that applies across all the industries, but then can be tailored in to meet the specific needs or requirements or operational modes of these individual subsectors. Right? So that's kind of my concept. And you can argue the VSM itself is a further abstraction, right? So we have VSM as one abstraction. VSM is applied to process industries, which all operate more or less the same way. There's the next abstract. It's not an abstract, it's the opposite of an abstraction. What's the opposite of an abstraction? A realization. And then, but still not terribly useful in its own right, but then get to a further level of realization of saying this is what you need to do for compliance-based industries like food or pharmaceuticals. Yeah. And this is there's numbers, right? This is the numbers are all more or less the same. This is Boston Consulting Group, I think, looking at digital transformation projects in the process industries. And the stories are that only 30% are deemed to be successful, right? 70% of digital transformation, moot point what we mean by that fail, these fail. And we're talking about big companies, we're talking about the Exxon Mobils of the world, we're talking about the Aramcos of the world, right? We're talking about companies that spend lots of money, right? And when we think about they're only getting less than a third return successful, and the hundreds of millions, if not billions of dollars that are being spent on digitalizing their industries and businesses to relatively little impact or effect. Right? And actually, there's a growing kind of weariness around this in the industry now. Sort of a lack of belief, a lack of faith. Okay, different way of looking at it. Now, this is a me and Penn slide, right? That we say we believe fundamentally it's because everybody tries to run these projects as linear ordered system projects, and they're not. They're complex system projects which are co-evolutionary, adaptive, and dynamic, and all those sorts of things. But I think it's probably more to it, right? So we want to kind of just look at this. Why do I think this model is really powerful? I think the way Martin would describe this is that organizations all have an anatomy. We call that organizational design. It's about having organs that have specific functional capabilities. And like the organs of the body, it's anatomy, right? Org design. We know a lot. If you go to business schools, we know a lot about that. There's huge degrees of sophistication and understanding about different organizational design models that serve different purposes and different things. On this side, when we bring those organs together, we use them to achieve certain things. Yeah, cardiovascular system, reproductive system, digestive system, multiple organs working together in synchronization and harmony to achieve certain effects. Right? And in the business organizational world, we have business process.
which would include my thinking just-in-time management, Toyota manufacturing system, total quality management. The list goes on and on and on and on for stuff in this space that we understand, is what I've thought about, huge bodies of knowledge, yeah? So we know this stuff, right? The one thing we don't have in organization business thinking is this model of neurology. We don't have a, well, what's the neurology? Now, neurology is what you, and again, I've talked with Angela about this, and when I think neurology extends into things like endocrine systems and stuff, it's the messaging systems within the human body, right? And how do we do that? And how does the neurology fit in some sort of harmony with both the anatomy and the physiology? Because obviously those three things have to work together, right? And they have to be, I don't know, symbiotic, or they have to at least be harmonious, right? And the fact of the matter is, there are, to the best of my knowledge, I ought to know because I'm one of supposedly the world's experts of this in the process industries, there are no real academic models of thoughts about what this looks like. State of the art right now is that every signal and every piece of information you get anywhere in your entire organization, you stick in something that used to be called a data lake, but they realize that's a bit of a misnomer. They now call it a data swamp. Right? You stick it all in the data swamp, and then you give anybody that's interested access to the swamp and say, go knock yourself out. It's all there. Right? And that's about the limit of sophistication we have here. There's a little bit of kind of something around things like edge compute and on-prem edge and cloud, right? So cloud is now confusing things. You have the old data cubes and data lakes, and now some ethereal cloud storage, which nobody really understands, right? And we have edge compute, but it's not, I mean, this is not terribly sophisticated. It's actually a pretty crude model for what we do with signaling and messaging through an organization by comparison with the intricacies we have on these other two sides. So it doesn't match. Now, when I think about the power of digitalization or digital transformation or digital or IT or IIoT or whatever you want to call it, to me, it's all about this. When you think about what's the digitalization doing, it's actually making this potential happen. Right? It's just all about messaging. Yeah. But we don't have a theoretical framework for how messaging in an organization works to support the physiology and the anatomy. And certainly among the process industries, I think it may be better developed in some of the service sectors and in discrete manufacturing and process industries. We don't have it. We're still trying to do it the old-fashioned way, right? Which is somewhat amoeba-like in things. So, point of today really is this kind of loop. It's really, I'm trying to, I'd like to engage interactively with you. In the process of doing that, I'll sort of talk about my perception of where things are at. And see what we get.
Okay, my interests mostly fit in the infrastructure sector, electricity. And at the moment, it's sort of staggering its way through becoming a smart grid. So they know they've got the potential for sensors and processing of data at all sorts of levels. They're not quite sure how to do it.
Yeah, absolutely.
So, I mean, does infrastructure data map onto process industry data?
Yeah, I would say it does. That's, I mean, if I go back to my model of I would have that all in this. Now, it's arguing it's sort of in between these two. Yeah. This is more about the generation. This is more about distribution. But water might fit in there.
Yeah, absolutely.
And electricity and other things.
Because increasingly, the electricity infrastructure is having to deal with the concepts of things like, well, storage, then electricity, there's the batteries.
Yeah.
They really don't know how to do that. And also, lots more embedded generation.
Yeah.
Lots more demand side management because of various market forces.
Yeah.
So there's a whole lot of stuff going on.
Yeah.
It's a bit of a wild west.
Well, absolutely. There's a whole lot of nuttiness goes on as well around things like commercial models of pricing because of that, because we don't know how to think about real-time information and data.
Yeah.
We're predicated on a world where electricity is electricity and all electricity is the same, therefore all electricity must be charged at the same rate. And as a result, we pay wind farms crazy amounts of money not to produce when it's windy because we've already got an overloaded grid. And we do this, but almost uniquely in the world, this kind of crazy peak load pricing premium that does, just nutty things.
Yeah.
Well, maybe it's nutty, maybe it's smart, I don't know, but I think it's partly because we don't really have a handle on how do we think about the information and the messaging in the system to then execute or initiate the right sort of action. We just don't know as an industry how to break that problem down. And I think VSM maybe.
Well, that was a question. I mean, have you taken a process industry you know well and tried to map it using the VSM?
Well,
have you ever done that?
Because that's part of the purpose of the presentation. So, okay, so I'll run through a couple. This sort of speaks to the why, right? Slightly different version of the same challenge, I think, or manifestation. I can't contrast. My model here is an aerospace engineer who works at JPL in California, right, which is where they drive the Mars lander from, right? So every day at work, that individual gets into work, and they look to see where is the damn thing, right? Where did it get to? And then they say, well, where do we want to get it to today? And they spend most of the day planning the process of how it's going to travel from point A to point B. They map it all out, and they even simulate it, they may run it, they do all sorts of things. And the objective by the end of the day is to get what they think is a robust set of instructions, which is beam up to Mars and press go when they go home. And it trundles along overnight. And then they get into work the next morning to see where it got to. This is periodic, discrete, slow, deliberate movement. By contrast, the process that same engineer goes through when they get in their car to either get to work or go home from work is a fundamentally different process. It's one where they know where they're going, they go until they get an alert to say traffic ahead, or well, look at that kind of kid running across the road, at which point they intervene, they operate in responsive immediate real. I call it runtime rather than real time because the IT folks get upset with real time as a statement, right? But it's a fundamentally more effective way of operating. Now, there are good reasons why this is done this way. Latency and bandwidth are real constraints. You can't actually, short of having somebody up there drive the thing, you can't drive it remotely.
How long does the signal take to get from
Well,
there?
it varies. It depends which side of the solar system, whether we're the same side of the solar system or opposite sides of the solar system.
But roughly,
I mean,
hours,
it's minutes.
okay.
Well, it can be minutes.
So there's no way you can
10 seconds
say-
minutes.
There's no way you can say it's a rocking
No,
train. I'll go
No,
around.
you can't. So this thing runs at an average speed of 0.5 mile an hour, right? An average speed. I don't know. I think that's its top speed is 0.5 mile an hour, right? Which you genuinely could walk a lot faster. Now, so there's good reasons for that, but this is where we want to be. Weirdly, we still run all of the process industries this way. Now, electricity grids, I'll grant you, is the one exception to that, right? Because there is no storage, therefore it has to be responsive. But I've spent a lot of my life on chemical plants, and we issue a plan for the following week for productions, hand it over to the plant, and then pretend that we're on the other side of the Atlantic and that we only have steam ships to actually convey information, right? We wait to the end of the week to find out what the buggers did, discover they didn't do what they were told to do, and then we have spent a week arguing about it, and then we give them another instruction for the following week, then ignore them for a week and see what the buggers did, what they told them to do, spend a week arguing about it, and the cycle repeats, right? So the question is, why can't we get to here? Despite huge amounts of investment in the technology, we couldn't do it.
Can I comment on this?
Yeah.
Gary's talks in his presentation about uncontrolled growth, and that's always bothered me. So we go back into the previous one.
Yeah. So what are we trying to achieve? We want to be faster.
Yeah.
We want to be quicker. Are we trying to be safer?
Well,
Are we trying to be greener?
Potentially. I mean, it could be any or all of those things.
Because for me, until now, when they put down the argument that we're doing all this stuff to protect the environment or give better service, sometimes I feel that this argument is either not true to the world or not justified well at this right.
Yeah.
I don't want to deviate the conversation, but I mean the reason we are doing it, for me, I miss it. I'm not suggesting that we need to travel to work and that's great. But sometimes if you have okay system, now you want to move it to that level. Is it true that that level is better for humanity than what we have?
Well, I mean, that's a great question. That like with any technology, depends on what you use it for. We can use it for good or for evil. We can be the Sith or we can be the Jedi, right? You know, we have choice and discretion. And, you know, given the nature of some of those companies in this, it's going to get used for both, right? Technology exists and it will get used for both, right? I'm being recorded, so.
Very nice. I'm already engaged. So neither of you would I trust within an inch of my life to actually use this responsibly, but then I also have to work with individuals and continue to work with individuals and companies in these industries who I know are desperate to try and make a difference and understand how. Right? And I'll put it to you that part of this is, you know, sort of an example of how this makes a difference is when we think about emissions, right? This is just an example, right? This is something that I originally developed when I was asked to work with a very big oil company on their circularity strategy, which I found intriguing. So, you know, how do you circularize oil? It's a challenge, right? Well, you can, it takes millennia, right? But anyway, one of the big issues, what we see in downstream manufacturing is real focus on embodied carbon materials going into packaging or raw materials or whatever, real interest and a willingness to pay a premium. But when we go upstream to the bulk commodity producers, they don't have the numbers. They can't tell you what's the embodied carbon of this load of plastic or this piece of chunk of metal or this lot of glass, right? They don't know. Well, they claim they don't know. They don't know. They don't know in part because what you can't do, you don't make this stuff as a box, you know, we don't make it as boxes of plastic. We just make plastic and it keeps coming. Yeah.
Just a point of information. So they know it for the carbon, it's a carbon border adjustment mechanism, right? And so they know it for what they think are heavy embedded, so all kinds of steel, all kinds of cement. And so there are, I think there are 7 categories.
They know it at this level. They have generic standards that are used for to differentiate between those things. But what they don't know is from that plant yesterday, what actually was it?
No, so
that's not known, and actually there's lots of studies that have been done to show, even on the supposed international standards, there's huge variability in price.
So you're right. I'm just pointing out it's changing with carbon border adjustment mechanisms. For these 7 groups of plastic, so they are requiring now you have to have audits. They have to produce a carbon thing, and then when the importer, if somebody imports it from India, let's say, if they don't meet the European value, then they pay.
Yeah, and the theory is great, but as somebody that's spent most of my life in that industry, believes me, the practice is something quite different, right? And even what we're measuring it against on those imports is based on little more speculation, right? Because there's no transparency, there's no visibility. So I'm going to roll through this. This is a piece of work that we did about how can you actually shift from a world where we use the standards, right? Okay, I am using this here and producing that, therefore my standard of body carbon is this, and then, but everybody that's doing the same thing works the same way, right? Yeah, it uses the same number. So there's no differentiation in the market. So, you know, Sabic and Dow and AkzoNobel's polyethylene, no, they don't all make polyethylene, but all come with the same number.
So there's no market.
So there's no market driver and no market mechanism. And there's no transparency because it's not being monitored. When it goes wrong on the plant, nobody on the plants is seeing it go wrong, so there's no corrective mechanism put in place. The stuff that you're talking about is all reported retrospectively, typically over quarters or annual basis. So what we know is that last year we did something really stupid in February, but by that point we don't know what. We certainly didn't know about it in February to be able to put it right and fix it. Right? So this is a process where we sort of project by using the actual runtime information that's available on plans, you can start and incrementally shift and work towards a place where you can sit eventually. Now, there's a lot of this.
You want to do it?
Yeah, no,
This one?
Just the arrow on the keyboard, pop up,
the left, yeah.
let's click with the mouse, John, click on the mouse on the slides. Yeah, now you can use it.
Oh, I've got it, yeah, I've got it. So, I've got it, John, it's fine.
Okay,
So, it's a step by step. As always, you can't just jump from here to there, right? It's a progression of the change, of the evolution. But we can jump through a process whereby we can actually get to doing runtime actual on everything where runtime actual is possible. And not all of these steps are easy, but there's a pathway that we can go through, which starts off by saying, just know what your runtime actual is where you are. Once you know that, you can ask the people that are supplying you what theirs is. We do dynamic data exchange for things like stock levels and other quantity metrics. So we could do this for embodied carbon, and eventually get to a point where we're using rules on the end of life stuff, which you can't do with runtime. You can't do downstream, what we call downstream stroke 3, because we don't know what's going to happen to it, or what's going to happen to it at end of life. But we can use rules there to actually get to something whereby an individual, at this point, an individual sample polyethylene can come, not only with its melt point characteristics and its opacity numbers and all the stuff that you already before, but also with its embodied carbon, which is an actual embodied carbon, which creates the premium.
Yeah, which presumably then you have some kind of encrypted, method of then doing the exchange and the transaction.
I'm not pretending this is simple. This is not the put. I'm just trying. What I'm trying to get to is the switch. It was really to answer Ian's question: is does moving from that periodic retrospective to runtime actual really generate any meaningful impact? I'm going to say here's a great example of how it could. I'm not saying it will. You can do all this sort of stuff. Now, that's one example for greenhouse gases. The other big example is around market responsiveness to flexibility. So I think one of the things that I was involved with was building a new plastics business, and we decided we were going to compete on the basis of being the most dynamic and flexible in Europe, meaning that when somebody desperately needs somebody, they would phone us first. And that's what you want. You want the first phone call, right? You don't want to be third in the list or fifth in the list, because by that point you can lost your opportunity to charge the premium for the desperately needed product. So we wanted to be first, but to be first, we needed to be able to give an answer now, not in an hour or a day. We'll get back to you tomorrow or next week. So we created, and I've got, if we're interested, I've got the whole process of how that would work in the step. Right? No, it's useful though to kind of look at where this all come from. So this is a story. This is actually about process control, but it's very similar to something we saw Julia put up on the screen this morning, right? So this morning, Sad looked at the shower and turned it on and froze himself to death, right? Then swiggled the temperature controller, got cooked, and finally got it right. Okay. This is like I used to teach process controls, and we're rattle through them to try and make a point. So what's going on? We have a process, right? So this is our, we call this the process. This is the process. It's the system that we're actually of interest in, right? We have measurement, right, which is all to do with that. Are we feeling hot, cold, or just right? Yeah. We have a set point, right? We call it set point in control, in process control. Set point is where we want to be. We want to be at right? But we have an error, which is how far from set point are we, which is right? We have an actuator, something that we waggle to change something, right? And we have an algorithm, right, which is our process model.
Yeah.
Now, actually, what I'll say is, one thing I would take issue with what we said this morning is that process model doesn't have to be an accurate representation of the system. That's one of the problems. We don't try and rigorously model, fluid mechanics and finite particle element. We don't do that. We just do some stochastic. Here's a dynamic interpretation of what actually happens. You just need to know the behavior. You don't need to have the fundamental first principles models.
So that's what we have, and we create something. Ta-da! You saw this yesterday, this morning, right? We have this sort of a control. You guys have all seen this, and there's your E's and your R's and your right. So, and this is really just introducing the way we tend to draw it. But again, you guys have seen this, right? You know this. So we end up with something like this: is a control loop where we've got a three-way valve into some sort of mixer. I'm going to say we've got a comfort measurement, right, which is our skin, right? We have a comfort controller, which is our head, and then we have an actuator, work on an actuator. And what we then do, okay, this is just helping people understand what I'm talking about. I know people will follow this, right? First point of control. And I think there's something, you know, as I go through this, I think actually there's something that feeds back into BSF as well. So I have my 8 golden rules of process control, and I'm going to highlight 3 of them. But this one, you can't control something you can't measure, right? And you've got to measure what matters, not what's easy. It's classic mistake, right? And any measurement you make is always wrong. It's also another fundamental rule. There is no such thing as accuracy in this sense. So what do we do about that?
So can you explain the last one? Last one.
Well, it's the challenge here. So one of the things we often see, you know, particularly if you're trying to do something like inventory control. So okay, you're doing battery storage, or the big one is we're trying to put gasoline in and out of a tank. So very often students, they say, well, just have 2 flow controllers, and you know what the flow in is, and make the flow out match it. And yeah, if in theory you could do that, so you have 5 tons an hour going in and 5 tons an hour going out, in theory that should balance the tank. People intuitively say that's what you should do. The problem is there's no measurement you make that will ever actually be right. There's always something. The one thing with all measurement is it's wrong. The more expensive, the more money you pay for the measurement, the less wrong it will be. But it will always be wrong by its very nature. Very often we're not even, when we're measuring flow, we're actually normally measuring a pressure drop. And then we're inferring a volumetric flow based on that pressure drop, and then we multiply by a density to get mass flow. So there are multiple error points on your points of inaccuracy and ambiguity, which means that what you think is happening is never what's actually happening. But you don't know how wrong you are. So you can't rely on the accuracy. If you're ever relying on the accuracy of a number, you're in a world of hurt and a world of trouble. What you need to do is look for something else that's going to change depending on how wrong you are. Is the tank going up or down?
Yeah.
If the tank's going up, you need to either reduce what's going in or increase what's coming out. And you might find that at steady state, it looks like 5 tons in and 5.5 tons out. Well, that's fine. Don't worry about it as long as the levels.
So are you just talking about not measuring the system itself, but just treating it as a black box?
Well, no, it's the fact that you can't. There is no such thing as an accurate measurement.
Yeah,
I
explained this in terms of the limited capability of human sensory. So you can't get it right.
Well, I can see on the 5 tons in, 5 tons out. It's never going to be exactly.
Yeah, it's never going to be exactly right.
You're going to get variations.
Yeah.
It'll either spill out the top or the tank will be empty or whatever.
Yeah.
So, but much more sense to use the cybernetics to measure some error between them. Just like a toilet system.
Yeah, absolutely.
Our objective is. Well,
what is that?
Even if it's not stable, you can still measure it. So you can't establish a consistent measurement.
Yeah.
So I accept it, but even if it's varying, if you have a very accurate machine or measuring the level, you can still measure.
Yeah, and it depends on the tolerance that you have when you measurement depends on the purpose of the measurement.
Yeah, exactly.
It's
I accept your. It can be meaningless to establish very expensive machines.
Could you not measure accurately when it's static?
Well, you'd hope, but even there's problems with liquids change volume and change density with atmospheric adjustments with temperature. You're never quite sure what's in there. How much water is there, how much the shapes of things, metals, metal, all that sort of stuff. But what we then do is we say, okay, well, this obviously isn't a great control system because it's actually somebody's head, right? So I'm cheating a little bit. So what we then say is, well, we can do better than that, right? So what we do is we put the temperature controls, we put a temperature measurement here, we put a temperature controller here. So now manually we're saying we want the temperature to be this, we look after this to close loop, right? Now, we call that, what we would call that cascade controller, right? Now, I'm suggesting this is starting to look a bit like recursion, right? Maybe, I don't know. But what we then do is we say, actually, but we don't like doing that, so because we don't like these kind of weird, goofy things, so we want two valves, and we get increasing degrees of sophistication, right? And actually what we've done here is by introducing a second measurement, we can control the second variable, so we can actually have both flow rate and temperature, but only if we measure both things. So measure two things, actually not both things, two things. Yeah. Two measurements means we can control two. One measurement we can control one.
Why did you say it's recursion? I get feedback, but why is it recursion?
Yeah, I couldn't see.
Well, maybe it isn't at this level. I think temperature to flow perhaps is. I don't know.
Okay.
But when we get
Where
where we're going to go next is when we say this is no longer a shower. This is an oil refinery. This is an oil refinery. It's one of a number of the fleet of oil refineries that are actually that make up that comprise an entire global company's manufacturing operations. You can sort of imagine layering and layering and layering on top. And actually that was always been our goal as we try to automate is how far can we go on the automation stack? Because what we don't want is lots of people having to enter lots of separates. Right? So what we want is something determining what that temperature should be, which is based on some sort of quality, which is then based on some sort of target production rate, which is based on some sort of inventory and market demand, which is based on, and you can go all the way up to the top level of the organisation, so you can understand the cascade of decisions. And what we've always kind of conceptualized, well, if you can understand the cascade of decisions, you should be able to close a loop on those decisions and automate it. Yet, there's always been a fundamental barrier or problem in doing it that I don't think any of us have ever really understood. Right? So I'll just sort of bounce through. Other thing that kind of runs into this is the path dependency. The history is really fundamental to this, right? We started off, this is the original control system. It was called a one-legged stool.
Yeah.
And this was in Dumfries, right, on a ammonium nitrate, I think it might have been glycerin, but an explosive plant. And his job was to turn the wheel to keep the dial where it should be. And the purpose of the one-legged stool was because it was the most boring job in the world. When he went to sleep, he fell off the stool, woke up again. No, seriously, you can see, look, it is a genuine thing.
It's like the guy in Metropolis who's doing the
Yeah. And actually, Metropolis is really good because this is an actual photograph from the first plant that I worked on. It was older than me when I started working on it. But I still did the first digitalization project for ICI. Some of you remember ICI, right? I did the first digitalization project on the shop floor for retrofit for ICI anywhere in the world, and it was actually this plant. Right? So it tells you about how recently that happened. This plant, these things are actually pneumatics. So there wasn't an electronic signal in here. This was, we blew air down a straw for about half a mile and inferred the flow rate. So going back to this no measurements accurate, right? We inferred what the flow rate was by where between 3 and 15 psi the pressure of the air at the other end of the straw was. Then what we had is these little bellows and levers and pivots, and we would move. We created a whole control algorithm called PID, proportional interval derivative, which is actually a mechanical computing algorithm where gain, proportional band, is where's the pivot on which you go. Integral is how full is the bellows, right? Which is pushing the lever one way or another. What we've done over the years is converted that into electrical analog, which we hated and nobody ever used. Eventually digitized, sort of in the late 90s, we created digital versions of the mechanical algorithm. We still use those, right? We do sort of run control plants like this. Now, what's happened is as we've now been able to collate information, all of the majors have built these buildings, supposedly a global operations centre. There isn't a single operating company in the world that's actually using their global operations centre for operations, because they've got it, and they find themselves in Riyadh or Abu Dhabi or Dubai in Texas, looking at these things going, we don't know what to do with it. What are we supposed to do with all this information? Like, how does that work? Seemed like a great idea. There's no ability. Aramco just have turned theirs, they've given up, turned theirs into an innovation centre. And they have 3D printers and stuff like that in there now, right? Because they just, well, spent a lot of money on it. It looks great. It's great for showing people around. It looks really glitzy, but they're not actually doing anything. Because they don't know how to, right? Because they haven't got it. So,
Well, presumably they don't have the algedonics, which are bringing up the signals that they need to focus on.
well, then there's all sorts of issues. Yes, I mean, that's part of it. I think that, John, you've just sort of articulated where I've got to, which is they just don't have anything close to a VSM level of understanding of what they're actually trying to achieve.
Go back to the other slide, it's a little anecdote. So I worked in this world as well, the world you're talking about there with all the panels. So days when we were doing DCS systems and SCADA systems, and they went to computer screens.
Yeah.
And suddenly there was this huge loss of information.
Oh, yeah.
Because what would happen is the plant would fail, something would fail, and the operator would notice that just before that happens, something happens over there.
Yeah.
That goes weird.
Yeah.
And then when they just look at the screen, they don't have that information.
Yeah. These were all what we used to call chart and pen recorders.
Yeah, there you go.
No, that's not right. Ink and pen chart recorders. There you go. Yeah, and what they did is they had, it was like a seismograph, yeah. And what a good operator could do, it was really interesting, they didn't know, they had almost no comprehension of why. But a good operator could stand in the middle of the room, this size of them all around the wall, they could spin the room and know, they just knew there was something happening over there, something was about to kick off down here. Because they had that time series information. When we went to this, and actually still a problem's not been solved, right? They now get a number now. And that time awareness that comes from pattern recognition and traces is completely gone. Which is totally changed. I mean, there's also, you totally changed the way we think about it. And again, I don't think we've got any of that right yet, even now. And then what we'll do is remove that, exacerbate the problem even further, and putting that data problem over here. We're way out of time here, guys. Let me kind of back this through. I'll get to the end of this section and we'll stop, right? Because what we then did, we created this thing called a DCS, right? Which is, again, one of the most misnamed pieces of equipment in the world. It stands for Distributed Control System, and it's categorically not distributed.
Yeah.
So, I used to work for this company. I was a kind of global competency domain lead for sustainability and production optimization. So, but you'll see what we have is down here, we have all of these are the things that are actually talking to the plant, right? The measurements, the valves. You then have this layer of stuff, which is the stuff that's doing the thinking, right? Receiving the signals, converting the signals, doing the thinking, then we have a display level. And we create this thing called the purging model. Level 0 is the plant itself. And essentially all of this stuff is in this level 0, 1, 2, 3. Then there's a level 4 and actually a level 5 that's above it, which is where you get into what the business is doing. And then what that means, sort of commercial operations, HR and all that sort of stuff in the top. And we created this model, and this is still pretty much the predominant mindset in the industry. Interestingly, at the time that I would think where this was created, hardware and software were synonymous because you ran the software on the hardware and everything happened on the same box, right? So nobody ever really knew whether this is a hardware or a software model. Whether this was like, if you like, process. Is this anatomy or physiology? If you like, nobody ever had that clarity. Obviously, what's happened today is any of this can be anywhere. Bounce signals wherever we want. But we still stick to this world, right? And then it kind of got more complicated because we then could start doing a whole lot. It wasn't only about operational processes, there's health stuff from reliability, there's safety stuff, there's environmental stuff, there's legislative stuff, there's physical information, there's all sorts of other information coming in, and suddenly that's becoming digitalized. So we digitalized the process. Well, we automated closed loop the process probably during the 1950s. We actually made that electronic in the 1900s. But since then, a whole lot of other stuff's become available with real-time measurement and what have you. And what we're trying to do is squeeze all of that into the one architectural model that we've got. So we're now trying to do reliability and safety. We're trying to do it all more or less. I'm taking a slide with this, but more or less in the same architectural model. Squeezing it all in, squirting, now we get to the point where we squirt all this stuff into the cloud with some sort of forlorn hope that it might be useful to somebody one day, and then get frustrated that it's cost a shitload of money. We pay Accenture or Capgemini huge amounts of absolute fortune to go and tell us what we should do with it, and then they leave and we can't remember what they said. And have to pay them even more to come in and actually maintain the systems. We're in that loop, right?
It goes into a data lake.
Well, yeah, or data swan. That's not a new one, right? So we then have this. Now I'm starting to say this is starting to look a little kind of system one mapping, right? But this is sort of recursive. I don't know whether it is or not. But it gets more complicated as all of a sudden reliability starts impacting on operations starts impacting on logistics is impacting on shipping and marketing and commercials, right? We're in this integrated world, and people are just drowning. But we haven't changed any of the underlying ways of operating at all. Because we don't know how to. Because we've got no model of decision making, we've got no model of neurology, is now my theory, right? So we just create, this is one of my favourite math things, it's bullshit, honestly. I'm not being recorded, sorry to anybody that sees this and recognises where it comes from. But we can create this kind of block diagram, but it's a bit of nonsense, right?
What's the multiple historians at the bottom of that diagram?
Well, okay, so this is at the plant level. What we've got a slightly goofy kind of architectural setup where we have a DCS, right, or a SCADA system just doing the runtime, real-time interaction controls. What we typically now do is we have a time series database, which we call a historian, right, where we spit most of that information into. But alongside that, the time series historians aren't great for storing relational database, relational type structures or discrete type event structures. So we have other databases as well. For example, we'll have often we'll have an energy management system inside the historian. We'll have a labs, we call it LIMS, laboratory information management systems, right? Because they don't really fit in the same data architecture. So from a software perspective, they don't look the same. We might have a super high-speed data log of the turbo machinery, because which is running at millisecond scan rates rather than the seconds and minutes of the process. So what we find is even down at this level, we've got blocks of data storage. Increasingly now, some of those are coming off. We call this on-premise. Some of those are coming off-premise into clouds normally, but nobody can quite knows what, why, and when. Obviously, putting stuff that milliseconds do that is an insanely expensive exercise, even now. But sometimes it's being processed, sometimes it's not, and some of it just sits because it's transient. You only have turbo machinery stuff. You don't store millisecond level data indefinitely. You store it for a week or two because it enables you to go back and do a retrospective on something that fails. Right?
But isn't this the key to it? Because this is the stuff that Stafford goes into in great detail about. I mean, even when he was writing back in the 60s and 70s, he was complaining about database companies just making huge profits, and there was no point whatsoever in storing huge amounts of data for huge amounts of time. And you need these alerting signals to generate the information to focus your attention. I mean, it's an entirely different approach to using knowledge.
Yeah. No, absolutely. And I mean, it's not lost to me that Stafford's early realizations came working in Scotland, right? Doing almost exactly this, right? You know, and probably asking very similar questions.
Yeah.
So I'm sure.
There's a lovely story he told me that his first job was doing exactly this, which was providing information to the chief executive of the steel mill.
Yeah.
And he used to take this telephone directory of information. And he told me this story that he used to take it on Monday morning, put it on the guy's desk. And this is everything we need to know about the plant in the last week. The guy said, "Thank you very much." Staff would go. Next week he'd come in and he'd have he said, "Here's this week's thing." And the guy would say, "Okay, thank you." And the previous week he'd be on the desk, hadn't been touched.
Yeah.
And the guy would do this, I put it in the waste paper basket, and the next one would go down. It was a complete waste of time.
It was. And then there was nothing. I used to
been in similar situations.
I think it was the worst job I ever had. Right? Because for somebody like me, knowing that the third Tuesday of every month is the Tuesday that I have to go in and do this specific task, and write it all out in Korean 5:13. But anyway, so I'll bounce through a thing. So when we built the polyethylene business, we kind of had to think about, well, what's the full decision stack? Now, this is not VSM before. This was trying to untangle some of the nonsense that we were dealing with, and just like, how the hell do we do this? And we created this model, which was a woman called Nina Thorne, who was prof of automation Imperial at the time. And we said, well, actually, there's basically 5 levels of activity we're trying to think about. Conservation management is conserve the planet, which basically means keep your balance your energy, balance.
I promise I'll help set up.
Okay. How long have we got? Started a bit late, so.
If they're still talking in the microphone,
Okay. Yeah.
This is Mark Johnson doing his performance.
Okay, well, we can see that. Yeah. So this is balance your mass, balance your energy. Because if you don't balance mass and don't balance energy, things go bang and people die. So it's a bad place to be. So that's the first thing we have to do. We don't care what's happening, just keep those balanced. The next one is make the stuff you're supposed to make. Right. So the next level is make sure you're making jet caro if it's a jet caro stream you're trying to make. Right. The next level up then is then and only then make the jet caro as well as you can. Right? But what does that mean? Life gets interesting at this point, because what does as well as you can mean? Does that mean maximizing profit in the instance? Does that mean maximizing run length for catalyst? Does that mean running into the next delivery or shipment of materials? What does that actually mean? When we've done that, we then want to be able to respond to changes when the market shifts, or when maybe this might be short term with the market change. Right? But one of the things that I've seen is, I think that's one of the rules here, is I've seen us on a supply chain that maybe takes 3 to 4 weeks beginning to end, purchasing an input for that cargo to actually shipping material at the other end. I've seen us respond to changes in spot price that take place over hours, and then respond back again. So there's a huge amount of noise induced here that never actually turns into anything real. And up at this level, we've also got a bunch of financial geniuses hedging positions against deviations in the market price, which when the market changes, we then apparently undo by shifting our production plans to match the real price rather than the hedge. There's a whole degree of kind of mad uncertainty.
5 minutes.
Okay.
No, 5 minutes.
Mad uncertainty. But again, I'm suggesting maybe this is the beginnings of a concept of what reflation might look like for these industries. I'm not saying it is, but
It's a great example. It's not the process industry, but it's very similar. Like when Spain got kicked off the grid,
Yeah.
because the price of electricity went low, so they decided they wanted to pull it. That changed the frequency. The frequency changed, it threw them off, and then they sent it back on.
Yeah, and all that sort of stuff happens. So but this gets quite hard. And it's like, at this point, I can understand why we can't close the loop. What I don't know is what the hell to do about it, and what the decisions are at the right levels, given we can now furnish them with real runtime information rather than the telephone directory retrospective of what happened last week. We haven't changed. People are still making the decisions they used to make. And getting confused, well, to an extent, and then all this is a little bit license.
And could you not simulate all of these various levels and then simulate scenarios and then see what happens as a result, and then on the basis of that decide whether the design is right and then going in.
You can, but yes, well, yes and no. I mean, I have a, yes, you can. No, yes, you can. It gets quite complicated. Well, one of the things that shifts here actually is what your understanding of what time is moves. For these first levels, time is a point. It has no dimensions at all. It's just a point. It's now. The only time that matters is now. Maybe you're going a wee bit back in time to understand. Maybe doing a little bit of dynamic path trajectory optimization. You're doing really sophisticated control. But really, time is now. When you go up here, you're starting to think of time as being. You're thinking about what's going to happen this week, next week. What am I trying to get to by the end of the month, by the end of the year? Particularly when you're doing involving regulatory issues, and just again part of to your point. Why do you want to go to runtime? Well, all the regulatory stuff is don't exceed this over 6 months or over a year, which makes actually running this really hard. Because what does this thing I'm going to do today is going to last 3 days? What impact does that have? I can't quantify it in an objective. There isn't actually an absolute right, because it all depends on what then happens for the next following year.
Yeah, but it's a heuristic opportunity.
Yeah. And then up here, you're actually talking about multiple versions of time. What you're really doing is sort of Monte Carlo type simulation up here. So you've got to have a mechanism for actually converting time as you roll through the levels, which then comes back to somebody said to me. It's about meaning. The important thing isn't the numbers, which is what we're hell bent on transmitting and reporting. The thing that actually matters is meaning. We don't have a like. Why? It's like, well, we said what we do is we drop a target, a goal, a number down to the level below, but without context. We don't explain why. The models we're using up here are always much cruder than the models we're using down here. So these are the least accurate models, but we're sending numbers down the path without explaining why. So we're not, because we don't know the why, what are we protecting against? What's driving us to that decision? Because we don't have context, we don't give the next level the autonomy, maybe, to adjust the target to a better number that still meets the context.
So you're talking about actually having local intelligence at the different, which can then interpret the intention of the messaging from above, interpret the meaning, and then they bring it into the context of that level of control, and then respond accordingly.
Probably. Possibly, totally. I mean, this is exactly sort of input I wanted from you guys. I mean, yes, I think it helped me clarify what the hell I'm talking about. But yes, it is. It is intelligence at the points of as you roll through recursive level.
And just go back to physiology, where this all came from in the first place. We do have an awful lot of subconscious processing that goes on, muscle memory, and all that kind of stuff.
Yeah.
Which is maybe what we're talking about.
Yeah. Just a couple of other things that I think are really powerful in this. I don't think in any of the things I've shown you introduces any concept of meta-system. Right? Any concept at all. I don't think that's in any way switched on. And I think we have an awful lot of this that somewhere becomes disconnected to this, and very little conscious design, conscious understanding of what the levels are trying to do.
I think we have an awful lot of that, but not smiling.
Yeah, probably that's probably true. Yeah.
Just
This is a few other questions that I kind of think about as we go through this. Is one thing I don't know. You're welcome to answer. Storage. Where do you keep stuff? We know where we generate it, but where do you store it? I don't know where that storage and memory. I don't know where that fits in the example. But that's a fundamental part of what's driving the thinking behind how we build systems.
So I know you put that is the way that they build modern plants where you don't come in and build it all up from scratch. You come in and say, right, we need a power module. That's a power plant. We've got a standard design. That's this standard. Are they not? That's a meta system.
Well, it could be. I mean, that's another interesting. We're starting to see modularization. That's what it's called in the industry. And we're starting to see a new. It's called open automation standards, so after standards, right? Or COPA is another one. Where we're starting to think about modularity of software systems that go with those different packages. But again, and I think this is where this stuff gets really powerful, because there isn't. I just don't see anything at all
which is, because
in the industry that says, okay, well, if you've got 15 different modules from 15 different suppliers do 15 different things, how on earth do you bring that together as a coherent plant and operate it as a single plant?
I can definitely help you with this. There definitely is something this level.
And then master data management, this is another, the whole industry gets super hung up on this concept of master data management, which is single point of truth, and then who has control and authority over single point of truth. And this creates the huge argument of wars between IT organizations, what we call OT, which is IT organizations. Anyway, I think it probably kind of stops with that. Let's go on to the other stuff. That's great.
Yeah.
But I'm intuitively, I know the answer is in, right? It's in this room. It's with the experience we've got. It's in the VSM. This is the seeds of an idea, and I'm still in the process of trying to frame out. Well, what do we need? What is none? Just haven't articulated. What are the questions we need to be addressed and given some thought to? I think the distinction between modularity versus what I call monolithic design practices is one of them, because you actually may end up in different places for good reason. You design in different places, but memory storage, I think that where does that live in a particular world of cloud edge on-prem, which is a weird complication that organisms don't have to deal with. We don't have a cloud option, right? We don't really have an edge option either. We only have on-prem as human beings, right? So there's some interesting questions in here that
It's funny because you've got a big wedding ring on. You don't store information there?
It's a skill that becomes a behavior, right?
Can I ask you, down in Corpus Christi,
Yeah.
right? So it's just refinery after refinery,
Yeah.
isn't it? So there's that many refineries there, they don't have a night time because the lights of the refineries just light everything up. What are the impacts of cloud down there on a system like that at Corpus Christi? Because you've got environmental impacts. We talked about this yesterday, weren't we? About the data cooling systems and everything else that goes on.
So the industry is going through a transition now. And we've done this progressively with technological advances. Right? Digitalization took us a long time. We air gapped the systems because we perceived them to be significant security risks. Right? So we air gapped them. And then realized actually the information that was on the plant was just too valuable, too useful for that to be credible. And we were employing people to look at the screen and type something into a different computer. Actually, there's a picture I've got. We used to have a lecture room probably 4 times the size of this. We had a little curtain rail at the top, right? And we employed somebody for every 2 hours. They on this little trolley, like a tea trolley. They had it was an old fax terminal. It would stop. It would look at all the instruments here and then type a number in and move along. The curtain rail was for the cable that connected it to what was then the modem, that connected it to I think it was a computer in Millbank or something, I don't know where it was. And they literally walked around the thing, typing numbers in. Now we've moved away from that now. We do have that sort of connectivity. But people, I'm going to say, people in the Middle East, huge sensitivity about anything going off-prem. Certainly, they'll allow data off-prem for commercial management purposes, right? No way at all there are. For any reason, right? That's part of where this idea of HMQ comes, right? We do the computer at the edge, report what outwards, which is a bit of I guess it's a bit like what's the challenge between system 1 and system 3? The compliant, not compliance, accountability.
That's real.
No, VSM.
And VSM, between system 1 and system 3, there's you've got resource bargaining, you've got the compliance one coming down, you've got accountability going
They
on.
all 3-star.
No, not 3-star. This is literally between. We draw between system 1 and system 3. We draw 4 arrows, right? Or 3 arrows, one which direction. Yeah. So you typically draw and we draw that one, which is the resource target, is this one, which is about compliance, right? So the standards compliance regulatory function, that one I think is called accountability.
Yeah.
Yeah. So we've sort of had that as an edge compute, accountability going up, like sort of. And this is sort of where I think the VSM can be really powerful in terms of formalizing our understanding of what communication pathways are, what function they're serving, and hence what they need to look like. And then one gets up on recursion is, I think recursion starts telling us what the appropriate decision making activity is at a different level. Because right now it's being used to flag something going wrong, then drill down into the specific. Essentially what you're ending up with is really senior executives in companies having the ability to drill into, see information about vibration levels, your radioactive vibrations on turbo machinery. Well, exactly, because they want to know that something's going wrong, because they think that's important. Nobody's really stopped it or why that. But there's a whole issue in this around trust in a way, right? And then, well, what are they going to do about it?
They'll pick up the phone and say it's not working.
Well, I know, but worse, what they do now is they phone the plant and say, do you know that you have your vibration problem on that machine? At which point they typically get told, piss off, yes, we do, and we're trying to work out why we do. But hopefully,
that vibration, so you need that data. If the people that are going to be monitoring it are the people who made the machine, and they're monitoring all of their machines all over the world, right? And they're saying, hey, this one's and that's where the architecture comes in, right? Because there's a different layer on this. It's sort of like Boeing planes flying from one place to another, right? We predict it.
No, absolutely.
And that's a use of the cloud.
Well, it's really interesting that when a lot of the, I mean, nobody's ever made this connection I've ever seen published it, but when we started to see significant maintenance and predictive maintenance capabilities on the process industries was about 5 years after the jet engine manufacturers shifted to power by the hour. And they were the people, it was the Rolls Royces of the world that worked out how to do this on-time measurement to predict, to anticipate machinery failure. And that's then rippled through into these industries. But fundamentally, there's a fundamental, if you look at the way a lot of this stuff gets architected, and then you say, well, what's the, roll it back to, well, what does it tell us about what we perceive successful level layers of management to be? It's that the top layers can do the job better than the bottom layers, but we haven't got very many of them because they're special. So we give them the ability to intervene. Totally wrong, in my view. Because, and also they sit there, they don't really know what else to do. They want real time. Everybody intuitively feels like, and this is your point actually. I think this is where your point has validity. Why does a VP of operations need to have real time information? Or this is why I like runtime. What runtime for a VP of operations should be mean something very different. Probably much slower time horizons than runtime for the power operator on the plant. But that's not what we're building. Building the same. Well, that's what I see, which is why people like I'm not building the glass balls and don't want to do them. Because we don't know. There's a lot of active faith stuff going on, investing in technology that's delivering nothing because they're actually not fundamentally changing the way they operate.
Well, actually, right, they're doing these things, but then there is a big push that's making happen, which is a fundamental change to the way the business runs. So take Schlumberger with anti-flare. They sell on the top of a kind of gas pipe, right? They sell the anti-flare valves for a small project. And they're doing
the recording. I'll tell you a story which I definitely want to have.
Okay, and they're doing anti-flare as a service now, right? And so what happens is they've got the information about that, right? And if there's a flare, their price, the price that they're paid goes down, doesn't it?
Yeah.
The pause. Oh,
So that's just great. What are we going to do?
Well, so